Bismillahirrahmanirrahim. Assalamu alaikum. Today's topic is matrix of the linear transformation, and the course is linear algebra and ODEs. And we are continuing towards our aim to complete the CLO 2 of our course, which is related to the study of vector spaces and linear transformation. So a quick recap that so far we have discussed about the linear transformations, their images and pre-images, and all of these topics and today's topic as well is mapped on CLO2 of your course. So the focus of today's lecture is on the fact that every linear transformation on a finite dimensional vector space can be represented as a matrix. And hence, after covering this lecture, we would be able to establish the fact that matrices are also linear transformations. So when we study about the linear transformation, a question comes into our mind that why linearity of a transformation is of great significance. Now, to answer this question, if we consider that V is a vector space and V and U are both the vector spaces, and the L is the linear transformation from V to U. And suppose that V is a finite dimensional vector space. So let's say that these are the basis vectors of V. And suppose that these are the image of the basis vectors LE1, LE2, and so on, LEN. These are the images of basis vector. Now, if L is the linear transformation, then since we know the effect of L or the action of L on these basis vector, then we can find the effect of L on each and every element of this space, because each and every element of this space can be uniquely determined through these basis vector. So from here we establish the fact that due to the linearity of L, it is enough to know the image of basis vectors to know the action of linear transformation completely. Now let's have an example. Let L be a linear transformation from R3 to R2 whose action is defined by these basis vector, that we have defined the action of L onto the basis vector of R3. So it maps this basis vector on this vector and like this. So what we have to do in this problem, we have to find the image of minus 3, 4, 2 under L, and this vector is actually the vector in R3. So we have to find the image of this vector by using the images of these basis vector under L. So solution for solving this problem. First, we see that since this vector belongs to R3 and these are the basis vector of R3, and every vector in R3 can be uniquely represented as the linear combination of basis vector. So minus 3, 4, 2 is uniquely written in terms of its basis vector. Now, if we apply linear transformation L on both sides and using the linearity of L on the right hand side of this equation, then you easily see that by using the law of preservation of vector addition and scalar multiplication, we can see that this right hand side is equals to minus 3 times L of 1, 0, 0 plus 4 times L of 0, 1, 0 plus 2 times L of 0, 0, 1. And if we simplify this by substituting the value of L of 100, that is the image of 100 under L is given by this vector. So we can say that this is equals to minus 3 times 2 minus 1 plus 4 times 3, 1 plus 2 times minus 1, 2. And after simplifying this, we achieve the image as 4, 11. So the image of L, image of minus 3, 4, 2 under L is 4, 11. So now so far we have done that if the action of linear transformation is given on the basis vector of V, then we can find the image of any vectors and we can determine the linear transformation completely. So if we want to see how this basis vector and how the matrix of that linear transformation can be determined, for this we put the basis vector of R3 into a matrix and we apply L on this matrix and we simply write the images of all three vectors here. So if we write here, then you can see that here 1, 0, 0 maps onto 2, minus 1, 0, 1, 0 maps onto 3, 1, and 0, 0, 1 maps onto minus 1, 2. And so this is the matrix of the transformation of these basis vectors. And by using this matrix, we can see that if we apply this matrix on any vector x, y, z, then we have this is the general form of this linear transformation, or you can say the general formula describe the action of linear transformation. So if we have the action of L on the basis vector, then we can obtain the general formula of the linear transformation. And the previously done problem, that is if we want to image of minus 3, 4, 2 now, then we simply put minus 3, 4, 2 in this formula here, and we obtain the image of minus 3, 4, 2 by using this general formula. So this is the direct problem, that we have the action of L on the basis vectors and we determine the general formula of L. Now if we are given the general formula of a linear transformation, then how we describe the matrix of this transformation. So for this, suppose this is a linear transformation and it maps R3 into R3 by using this general formula. So we need to find the standard matrix that represents L. So why we call this as a standard matrix? We call this as a standard matrix because to obtain this matrix, we use the standard basis of R3. As we have discussed many times that there are many bases in R3, that any three-dimensional vectors, those are linearly independent, can generate R3, but the standard bases are taken to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that is why we call this matrix as the standard matrix. So if we see the image of this vector under using this formula, then we obtain 1, 0, 1, and the image of this vector is 1, 1, 0, and this vector maps on 0, minus 1, 1. So if we write these three vectors in the column, then we obtain 1, 0, 1, 1, 1, 0, and 0, minus 1, 1. So this matrix described, and we write this matrix A that describe the action of L, and this matrix describes the action of linear transformation L. So if we summarize these concepts, then we obtain a theorem that says that if L is a linear transformation from Rn to Rm, then there exists a unique M cross N matrix A such that the action of L on the vector x is equal to the action of A on the vector x for every vector x in Rn. So the dimension of matrix will be M cross N because it will have N columns, because the columns are the basis vector of Rn, and it has N number of rows because if we see in the previous example, this example, then you can see here that this linear transformation L is from R3 to R2. So this matrix is 2 cross 3 matrix and it has 2 rows and 3 columns. So this result basically telling us that if we are mapping Rn into Rm through a linear transformation L, then the matrix has the dimension M cross N. So now we discuss some important transformations that usually used in computer graphics and their matrices. So reflection in R2 through x-axis. Now first of all, in the subsequent section, we whenever talk about some transformation and we try to determine that transformation, we try to see that what is the action of this transformation on the basis vector. So of course we are talking about the R2. So basically reflection is an operator because reflection maps R2 onto R2. So if I call this reflection, then it maps R2 onto R2, and I want to see that how it maps these basis vectors I and J. So I want to see the action of this transformation on the vector 1, 0 and the action of this transformation on 0, 1. So if we see here, the reflection is through x-axis. So any vector on the x-axis has reflect as its own, and so it has remain unaltered under the action of the reflection. So the action of reflection on 1, 0 is 1, 0. Now any other vector that is above the x-axis has the reflection below the x-axis. So the vector j must be equal and opposite reflection, that is 0, minus 1 here. So in this way, reflection maps 0, 1 onto 0, minus 1. So again, if we write these two vectors in the columns, then we obtain a matrix 1, 0, 0, minus 1. And this matrix A represents the reflection in R2 through x-axis. Now suppose we have a triangle. So we can also determine the general formula of this reflection transformation. For example, if we apply A on some vector x, that is we apply 1, 0, 0, minus 1 on x, y, then we get x and minus y. So basically this is the general formula of reflection, that if this A, that is the reflection transformation applied on xy, then it gives us x minus y. So this is the general formula. So suppose we have a triangle that is determined by these 3 points. So suppose we have this x-axis and y-axis, x and y axes here, and suppose we have this point -1 and let's say 4 here somewhere, 3 1, so 3 1, and the next point is 2 6, so 2 and 6. So let's say this is a triangle, and we want to see that after reflection what is the image of triangle when we reflect this triangle through x-axis. So if we see that the matrix, when we apply this matrix on some vector xy, then we have the vector x minus y. So this matrix, when applied on -1 4, it gives us -1 minus 4. And when this matrix applies on 3 1, it gives us 3 minus 1. And when this applies on 2 6, this gives us 2 minus 6. Of course, we are applying a here. So these are the reflected vectors. So when we draw these vectors, -1 minus 4 is somewhere here, 3 minus 1 is here, and 2 minus 6 is here. So we can see that this is the reflection of this triangle through x-axis. Now as exercise, you may try the matrix of transformation for reflection through y-axis and reflection through the line y is equals to x. Now K shear in x direction. What is K shear? The shear basically is a transformation that keeping one direction fixed. For example, it keeps x direction fixed because we are taking a shear in x direction, and every other vector is translated or dragged towards the direction of x. And so we can say here that if this is the vector I and this is the vector j, then this vector j will be dragged to some k. So this one is dragged or pulled towards this, and this vector transformed onto this vector. So if we see here, then let's say S is the shear transformation, then we apply shear on 1 0, then it remains 1 0. And if we apply S on 0 1, then it becomes so k times 1. So here, if we write the matrix of shear transformation, K shear, K unit shear, so this will be 1 0 and K 1. So this is the general formula, x plus ky and y. So we can also see that if we have a, let's say, a square and we want to apply shear with k is equals to 3, then this point is 2, 0, this point is 2, 2, and this point is 0, 2, and this point is 0, 0. So it maps 0, 0 onto 0, 0, of course, because this transformation is linear transformation. This transformation maps 2, 0 onto 2 plus 3 into 0 divided by y is 0 here. So we have 2, 0. So it maps 2, 2 on 2 plus 6 and 2. So it is 8, 2, and it maps 0, 2 on 6, 2. So these are the vectors. So if we see this vector does not change, this vector does not change, 2, 2 maps on 8, 2. So 8 is somewhere here, very large. So 8 is somewhere here, and 2 is again this point, and 6, 2, that is this. 6, 2. So 6 is somewhere here, and 2 is here. 6 here and 2 is here. So this vector comes to this vector, and this vector comes on to this vector, and this is the sheared square after we apply this shear transformation with k is equals to 3, and this shear is in x direction. So now we move towards the rotation transformation, rotation in R2 counterclockwise through an angle of theta. So again, to define this rotation transformation, we first see the effect of this rotation. Let's say I call it R2 in 2 dimension through an angle theta counterclockwise. So if I have this xy plane, x-axis, y-axis, this vector I, this vector j, or you can say E1 and E2 that we usually do. And suppose these vectors rotated through an angle of theta. So again, this becomes x prime, and this y becomes y prime. So what is the effect of this transformation on the vector 1, 0 and on the vector 0, 1? So if we see here, then this is 1, 0, and if we see here, then if we draw this perpendicular, then this side is equals to cos theta and this side is equals to sine theta. So the component of this vector will be cos theta and sine theta. Now here if we see, then this angle is theta and this is the opposite side. So this side is sine theta and this side is cos theta. And since this is in the negative x direction, so this is minus sine theta in fact. So this 0, 1 vector maps on to minus sine theta cos theta. So if we put these vectors into a matrix form, then we obtain the matrix, rotation matrix through an angle of theta counterclockwise. So we are taking the angle here counterclockwise. If you use the rotation clockwise, then there would be some difference in the sign, and you can also obtain the rotation clockwise. So this is the matrix of rotation in 2 dimension. So this is the general formula, and you say that you see that these are the component of this vector. So now you can see here, if we apply the effect of this rotation onto some, let's say, curve. So I am taking a simple curve, a parabola, and I am describing this parabola by using 3 points, 1 1, minus 1 1 and 0. So this is the parabola. This point is 1 1, this point is minus 1 1. So when this, and through, we rotate this parabola through an angle of theta. So if we rotate through an angle of theta, then this matrix of transformation becomes cos theta is 0, sin theta is minus 1, 1 and 0. So this is the rotation matrix when we rotate through an angle of 90 degrees. So here angle of 90 degrees. So this is 90 degrees angle rotation, and if we apply this rotation matrix on 1 1, then it gives us minus 1 1. And if we apply this on minus 1 1, then it gives us minus 1 minus 1. And 0 0 remains the same because this transformation is linear transformation. So this point maps onto this point, and this point maps onto here, that is minus 1 minus 1. So our parabola becomes this after transformation. So we can take some other color here so that we can easily recognize it after rotation. So this is the parabola after rotation. Now, all of these transformations can be extended in 3 dimensions, but I am doing here just the rotation in R3 about the z-axis, and again we are taking the counterclockwise angle theta. So again we want to know the action of this rotation on basis vector. So suppose we have this 3-dimensional coordinate system. Here is the vector E1, the basis of direction of x, or you can say vector I, vector j, and this is the third vector k. So rotation here in 3 dimensions through an angle theta, when we apply this rotation on the basis of R3. So you can see here that since the rotation is about z-axis, so everything that is on z-axis will remain same. So the z components will not change, and also the vector along the z-axis will also not change. So this vector remains the same. Now the angle of rotation is theta, and it is counterclockwise. So again, we do the same thing that we did in the rotation in R2, and this is our new coordinate system x prime and y prime after the rotation of angle theta. And again, if we see, then this side is cos theta and this side is sine theta, and so the component of this vector after transformation will be cos of theta, sine of theta, and 0. And similarly, you can see here that this side becomes sine theta with a minus sign because here x-axis is negative, and this side is cos theta. So this is again minus sine theta, cos theta, and 0. So if we write these three columns, these three vectors in the column of a matrix, then we obtain the rotation matrix in 3 dimension. So this is the rotation matrix in 3 dimension. This is the general formula. You can multiply it and write it in the simplified form. Now as exercises, you can derive the rotation matrix in R3 about the x-axis. Again, the counterclockwise through an angle of theta. So in this case, the x vector remains the same and the other two will transform. And you can also do the rotation along the y-axis, and you can find the k shear in y direction in R2. So these are the exercises from today's lecture, and also I will upload some exercises through the book on LMS. So thank you very much for your attention.